a particle confined in a 1D box between x is equal to 0 to x equal to L is perturbed by a constant potential V on the left half of the box, that is from 0 to L by 2. Okay, the constant potential is V between 0 to L by 2, and by a constant potential V by 3 on the right side of that is L by 2 to L. If it is so, what is the first order correction to the energy of the ground state? First order correction to the energy of the ground state we need to find out. Okay, this question appeared in 2024 December. Okay, right. So how to proceed? Listen. Since it is a 1D box, okay, you know very well in the normal 1D box, from this is actually x-axis, x value for the box is 0 to L, and we all know that outside the box potential is infinite. But in this problem, there is a perturbation. Okay, the perturbation is that, see, this is middle of the box, say x equal to L by 2. From 0 to L by 2, the potential is not 0, but it is constant. The value of potential is V. Okay, so let this be the potential V. Up to the middle of the box, the potential is V. Okay, this potential is actually V. Then on the and V by 3 on the right side, right half of the box. From L by 2 to L, the potential is V by 3. So let me draw like this. From L by 2 to L, the potential is V by 3. Okay. So due to perturbation, right, inside the box, the potential is constant with the value of V up to left half of the box, and the right half of the box, the potential is constant, the value of the potential is V by 3. If it is so, what is the first order correction to the energy of the ground state we need to find out? Okay, yes, how to do this? Right, it's a very simple problem. The usual way of doing this problem is that the first order correction to the energy of the ground state is equal to, the general formula is this. Let me write the general formula. First order correction to the energy of any nth state is equal to bra of nth state wave function in the unperturbed system, then perturbation operator, then nth state wave function in the unperturbed system. Okay, this is the general formula. Now we have a perturbation. The perturbation is up to left half of the, up to L by 2, 0 to L by 2, potential is V. Then the remaining half, the potential is V by 3. So we can split this integral into two parts. Okay, the left half we have the ground state wave function. Here n is ground state, so I'll just write ground state wave function. And okay, let me write the potential ones, then we'll split it into that. Okay, so perturbation operator, then the ground state wave function. I'll write the formula once, right? Then I'll split it into two integrals. You know, this is an integral, but now I have to split the integral into two parts. One is 0 to L by 2, the other one is L by 2 to L. So integral 0 to L by 2, that is for the left half. Okay, the ground state wave function, you know very well the ground state wave function for particle in 1D box in the unperturbed box is that square root of 2 by L sine, since it is the ground state, n value is 1, so n pi by L into x. This is the ground state wave function, right? Ground state n equal to 1. Okay, ground state wave function in the unperturbed system. Then for the left half, the constant potential, the perturbation is V, right? Then the same wave function we have to write square root of 2 by L sine pi by L into x into dx. This is for the first half. Then for the second half, let me write here plus integral 0 to, I'm sorry, for second half it is L by 2 to L. Okay, second half of the box, L by 2 to L. Then psi ground state wave function is same, square root of 2 by L sine ground state wave function for particle in 1D box. Then for the second half, that is for the right half, we have a perturbation with a constant potential V by 3. So the perturbation is V by 3 into square root of 2 by L. Okay, because we have tried the same wave function again, sine pi by L into x into dx. Okay. So for the first integral, we have square root of 2 by L. Okay, anyway, potential is constant. Okay, potential is constant, so keep it out, V into square root of L 0 to L by 2. Then we have this wave function psi n naught. So let me write this as such, psi ground state wave function, and again psi ground state wave function, okay, into dx, right? And you know very well, in the case of particle in 1D box, all the wave functions are real functions. There is no imaginary quantities, right? So all the wave functions are real functions for particle in 1D box, right? Therefore, instead of writing psi star psi, we can write simply psi. Okay, actually speaking, this should be psi star, but in particle in 1D box, all the wave functions are real functions, so psi star psi are one and the same. Then plus in the second integral, the constant potential is V by 3. I'll take it out. Then from L by 2 to L, in the same wave function, psi ground state wave function into psi ground state wave function into dx. Okay, this is nothing but psi star psi or psi square. Psi square will give you the probability, but now the probability is from 0 to L by 2, so it is 1/2 of the box, correct? Total probability is 1. For 1/2, the probability is 1 by 2. So V into, for 1/2 of the box, for left half it is 1 by 2 plus V by 3, and for the second half, see, this is again probability, right? Probability from L by 2 to L, that is for the right half. For the right half also, the probability is 1. Okay, you know very well, in all the state, probability in the left half and should be 1, so should be half, and the probability in the right half should be half. Okay, therefore total probability should be equal to 1. Now what is the answer? So this is V by 2 and this is V by 6. Okay, so we'll take LCM 6. So this is 3 into V and this is V. So 4V by 6 or 2V by 3. This is the first order correction to the energy of the ground state. Okay. See, we can also do in a simplified manner. So the trick is that this trick is applicable for particle in 1D box. Listen, it's a very simple one. So we need to find out the first order correction to the energy of the ground state. Okay, for particle in 1D box, n equal to 1 gives you the ground state is equal to, now for the first half of the box, potential is constant. Okay, what is the potential? V. Okay, what is the length of the perturbation? For potential V, the length of perturbation is 0 to L by 2. 0 to L by 2 is nothing but L by 2 length. Length of the perturbation is L by 2 divided by, what is the length of the box? Length of the box is L. Okay, plus, and in the second half, the potential is V by 3 into the length of this perturbation, L by 2 to L, the length is half L by 2 and box length is L. Okay, so if you simplify this, you will get V into 1 by 2 here, L cancel, plus V by 3 into, here also L get cancel, get 1 by 2. So we will end up with V by 2 plus V by 6. Okay, if you take LCM and simplify it, you will get 2V by 3 as the option. Okay, you will get 2V by 3. Right. So here I'm using the shortcut that you just write what is the constant potential available into length of the perturbation divided by length of the box. This is the idea. Okay. So for this question, the correct option is option B, 2V by 3, right? So next question, for a quantum particle in a one-dimensional simple harmonic oscillator, average value of x square, also called expectation value of x square, is h cross into n plus half into 1 by m into omega, where omega is the angular frequency. And the average value of px square is m h cross omega into n plus half for the quantum number n. For the quantum number n, this is the average value of x square and this is the average value of px square. The question asked here is the product of uncertainty of position and momentum for n equal to 1 is, okay, and 4 options are given. This question appeared in 2024 December. Right, listen how to proceed with this problem. See the problem given, the system given here is one dimensional simple harmonic oscillator, okay, and they are asking the product of uncertainty in position, that is delta x, and momentum, that is delta p, okay, actually speaking delta px, right, and the product of these two for n equal to 1 state, for n equal to 1 state. Okay, we need to find out this product for n equal to 1 state, right? Yes, very simple. See, you know very well the uncertainty in position or delta x is nothing but equal to, it is nothing but standard deviation, right? Okay, standard deviation, which is nothing but square root of average of x square minus average of x the whole square. This is the formula. Okay, so this is general uncertainty formula, right? So delta x is equal to our standard deviation formula. Standard deviation of any variable equal to square root of average of the square of that variable minus average of that variable square. Okay, and you know very well in the case of 1D, one dimensional simple harmonic oscillator, the average value of position, on average the position of the oscillator is 0, and on average momentum, okay, is also 0 because the oscillator can move in to and fro manner. Therefore momentum in one direction is positive and momentum in the other direction is positive negative. Therefore the net momentum is 0, and on average the momentum of the oscillator is 0. Okay, this we know. Now what is delta x? Delta x equal to square root of, okay, so we have average of x square. Since x is 0, so this becomes 0. So delta x is nothing but square root of average of x square. So which is nothing but average of x square is given. What is that? H cross into n plus half into 1 by m into omega. This is delta x. Take note. Yeah, in a similar manner, we should find out delta px. Okay, standard deviation in the x component of momentum, which is nothing but square root of average of px square minus average of px the whole square. As I said before, as a average of px is 0, therefore this becomes 0. Therefore uncertainty in the x component of momentum is nothing but square root of average of px square. Okay, and average of px square is given, so it is nothing but square root of m h cross omega into n plus half. This is average. This is the uncertainty in the measurement of momentum, and this is uncertainty in the measurement of position. Now we'll multiply this, we'll get the general formula. In the general formula, you place n equal to 1 or you put n equal to 1, you'll get what is the product of the two uncertainty for n equal to 1 state. Okay, so I'll do it in the next page. Just copy down. Yes, how to proceed? Listen. So what I'm going to do, I'm going to multiply these two. Direct formula also I have given. Okay, so you can use that also. But how to get the formula is very simple. So delta x. Suppose if you don't remember the formula, you can use like this. Delta x into delta px. Okay, what is delta x? Delta x is equal to square root of h cross n plus half into 1 by m omega into delta px is square root of m h cross omega into n plus half. Okay, so I am going to multiply. We have square root in both the part, so I'll take a single square root and multiply this. H cross n plus half into 1 by m omega into m into h cross omega into n plus half. Okay, everything is within the square bracket. M cancel, omega cancel each other. Okay, so now we left with n plus half whole square. N plus half into n plus half is n plus half whole square. When you take square root, it becomes just n plus half. H cross into h cross is h cross square. If you take square root, it becomes h cross. So this is the general formula for the product of the uncertainties in position and momentum. And this is the formula we use for one-dimensional simple harmonic oscillator. It gives you the product of uncertainties. Right, now for n equal to 1 state, what is the uncertainty? Delta x into delta px. Okay, that gives you, put n equal to 1 here, 1, so plus half, it is 3 by 2 h cross. 3 by 2 h cross. Take down. So the correct option for this question is option.
Yeah.
Okay, yeah, good. Take down. Right. So the next question, for an electron in an hydrogen atom with azimuthal quantum number L equal to 1 and magnetic quantum number M equal to 1, the angle in degrees between the z-axis and the orbital angular momentum vector is. Just go through the question carefully. Okay, for an electron in hydrogen atom, the azimuthal quantum number is L equal to 1 and magnetic quantum number is M equal to 1. They are asking the angle between the z-axis and the orbital angular momentum vector is. Okay. Yes, how to proceed with this? Listen, it's a very simple one. You know very well that, say, I'll take this as z-axis. Is the z-axis. Okay, and let us take this as, say, say this is the x and y plane. Okay, assume that it's xy plane, right? And you know very well, uh, total angular momentum is equal to square root of L into L plus 1 into h cross. This we know. Okay, and z component of angular momentum is m into h cross, right? Since L is equal to 1 here, if I put L equal to 1 here, okay, if I put L equal to 1 here, I'll get 1 into 1 plus 1, that is 2, so root 2 h cross. Okay, so for our problem, L value, that is total angular momentum, is square root of 2 into h cross. And what is the z component of angular momentum? Z component of m value is 1, so it is 1 into h cross, that is h cross. Okay, generally speaking, observe carefully, generally speaking, right, we should draw, listen, for L is equal to 1, what are the values of m possible? Plus 1, 0, minus 1. There are three orientations. Angular momentum vector takes three orientations in space. Okay, what are the three orientation? One is m plus 1, other one is m0, another one is m minus 1. Okay, so what we should do, if m is plus 1, see, if m is plus 1, then Lz value is h cross, correct? right? H cross. So in the z-axis, let us take some distance. Say this distance is plus h cross. Okay, this m is equal to plus 1 h cross. Then listen, I'll draw a line here. Then from the origin, you draw a line to this line, such that the length should be um, root 2 into h cross. Okay, first I'll give you the general formula. So the general formula is this. So this length, z-axis length is m h cross. This is called the z component of angular momentum, and this is the vector angular momentum, total angular momentum vector. The value of this is square root of L into L plus 1 into h cross. Okay. Now the question asked here is, what is the angle between these two, right? And you know very well, if this is theta, this should be opposite side, and here we have 90 degree. So this is hypotenuse, and this is adjacent side. Now we need, you know very well, the angle which is connecting the adjacent side and the hypotenuse is cos theta. So cos theta is equal to adjacent side, which is m into h cross, divided by the hypotenuse, which is square root of L into L plus 1 into h cross. Okay, so and h cross we can cancel. Therefore, let me write the next page. Therefore, the general formula is cos theta equal to m by square root of L into L plus 1. This formula is applicable for any m value and any L value. Okay, take down. Now, in the given problem, L value is given as 1. So I have given the general formula. L value is 1 and m value is also 1. If both are plus 1, L value is 1, m value is plus 1. So what is cos theta? Cos theta equal to, in the place of m you put 1 divided by square root of 1 into 1 plus 1, 1 into 1 plus 1, which is nothing but 1 by square root of 2. Okay, which theta angle for cos theta will give 1 by root 2? Anyone tell me?
45.
That's
Yes,
right.
sir.
So theta should be equal to 45 degrees. It's a very simple one. Okay, so the correct option for this question is option B. It's a very simple one. This question appeared in 2024 December, right? Right. A correct statement which always holds good involving unperturbed energy for the ground state, first order correction to the ground state, second order correction to the ground state, perturbed energies for the ground state is, okay, E0 is the exact ground state energy is given. Now we need to find out uh, the correct statement which always holds good. Okay, out of these four, right, we need to find out the correct statement. Right, the first one, listen, this is the exact energy or the unperturbed energy. Unperturbed energy, first order correction and second order correction. This sum, is it always greater than E naught? Okay, observe carefully. Suppose this is the first unperturbed ground state energy, right? And first order correction to the ground state energy, right? We use this formula psi naught H operator prime, perturbation operator psi naught. See, this integral can be positive, this integral can be negative, this integral can also be 0. Observe carefully. Whereas second order correction to the ground state, this integral, okay, you'll get an integral. Let me write the integral first. M naught equal to n square modulus should come psi m naught H operator prime psi n naught square by En naught minus Em naught. I have given this formula already, but for the ground state, this value is always negative. Observe this carefully. Okay. So if ground state, see sum of these three, is it always greater than 0? Where E0 is the ground state energy, exact ground state energy, is this sum always greater than 0? Not necessary. Why? Because second order correction is for the ground state is this is always negative. Okay, this can be positive or negative or 0. It can be anything. Therefore, the sum of these three, okay, may be greater than E naught, maybe less than E naught, maybe equal to E naught. Okay, so it can be of any value, right? So option A, listen, sum of these E naught over the ground state, first order correction to the ground state, second order correction to the ground state, this can be less than 0, okay, or equal to this. Sometime it may be greater than 0. It all depends on the magnitude of this. Okay, suppose the first order correction is positive with a high value, then even though this can be negative, the value can be positive. It depends on the magnitude. Okay, therefore it is always greater than E naught. This is wrong statement. Okay, this can be greater than, this can be less than, this can also be equal to 0. So this is a wrong statement. But we need to find out the correct one. What about this? Listen, sum of these two. Is it always greater than 0? Not necessary. Why? Why? Because the first order correction may be sometimes 0 also. Suppose if this is 0, then you will get the E naught, which is, see, in the problem they are asking greater than 0. Okay, is it always positive? That we cannot say. Why? Because first order correction value can also be negative. If this is negative and negative value, suppose the negative value is large in magnitude, then the sum of these two may be less than 0 also. So this is also wrong. Okay, and in option C, see, the ground state energy plus the first order correction, yes, this can be greater than or can be equal to, sometime it can be less than E naught also, sometime it can be less than E naught also, but in general for the ground state this sum is, is generally greater than 0, greater than E naught. So this may be correct. What about option D? Second order correction to the ground state. See, greater than 0 means positive. No, second order correction to the ground state is always negative. So this cannot be. This is a wrong statement. So out of three out of these options, the option C is the only probable answer. Okay, so the correct option for this question is option C. Take note. Okay, this is the next question. A hydrogen atom is in the state, okay, hydrogen atom is present in some state psi, which is square root of 8 by 21 psi 200, square root of 3 by 7 psi 210 plus square root of 4 by 21 psi 311. See, psi 311, psi 210, psi 200, they are all eigenstates of hydrogen atom. It's given clearly. See where psi NLM, psi NLM are normalized eigenstates. They are all eigenstates. What is given here is the hydrogen atom is now present in a state which is the linear combination of these three states. Okay, then what's the question asked here? If L square of the total angular momentum, if L square is measured in this state, the probability of obtaining the value of 2 into h cross square is 2 into h cross square is. So what is the probability of obtaining the value 2h cross square is? Okay, that's what we need to find out. And this question is appeared in 2024 June, but this is not from chemical science, this is from physical science, physics. This question is asked in physics. Observe this carefully, how to do this. You know very well, the magnitude of L square Okay, I'm just giving you the magnitude. Magnitude of L square is equal to L in, I'm sorry, it's small L into L plus 1 into H cross square. This is the formula. Okay. So if you measure L square operator on this state, this is the general formula we get. Now we have three states given here: psi 200, psi 210, psi 311, where the first value corresponds to N, second value corresponds to L, third value corresponds to M. So here L value is 0. If I put L 0, I'll get the angular momentum, square of the angular momentum is 0. If I put here L equal to 1, if I put L equal to 1, 1 into 1 plus 1, 1 into 1 plus 1 h cross square, I'll get, yes, I'll get 2 h cross square. So this state will give me 2 h cross square. And what about this? Here also L equal to 1, see, L equal to 1. So this state also will give me 2 h cross square for L square. So if I measure L square on this state, this will give 2 h cross square. This will also give 2 h cross square. Now, what is the probability of obtaining 2 h cross square? Okay, so probability of getting 2 h cross square for L square measurement is equal to, very simple. Listen, you need not consider this state because this state does not give 2 h cross square. Only these two states, that is 3210 and 311, will give 2 h cross square. So what I'm going to do, you see the coefficient, square the coefficient, square of 3 by 7. Okay, this will give you probability of finding 2 h cross square in this state. Okay, for this state, what is the probability of getting 2 h cross square, which is nothing but square of this coefficient, plus what is the probability of getting 2 h cross square in this state, which is square of this coefficient, square root of 4 by 21 square. Okay, but you should be little careful that square of this coefficient and this coefficient and this coefficient should be equal to 1. Observe this carefully. That, because then only this wave function become normalized. For the normalized state, okay, see, if the wave function is normalized, if this wave function is normalized, then you can take the square of this coefficient plus square of this coefficient as the probability. Okay, so that we have to check it. Okay, so you do that. Okay, I'll just give you this square root of 8 by 21 square plus if you take square, you'll get 8 by 21, right? 8 by 21 plus 3 by 7 plus 4 by 21. I'll just leave it to you. You check whether this value equal to 1 or not. You just check it. If it is so, then this state is a normalized state. If it is normalized state, then we can find probability directly using this. Why I am taking only these two coefficients? Because only these two states will give me L square value as 2 h cross square. So if I take square, I'll get 3 by 7 here. If I take square, I'll get 4 by 21. So LCM is 21. 3 times, so 9 plus 4. So the answer is 13 by 21 is the answer. Okay. So for this question, the correct option is A. Right? Take down. Yeah. What the question asks here? A particle of mass m is in a cubic box of side A. So cubic box of side A. The potential inside the box is 0. It's a usual box, and infinite outside. Good. If the particle is in an energy eigenstate with the energy equal to 7 pi square h cross square by ma square, then a possible wave function is. Okay. Right. How to do that? See, the particle is in this level, in this energy level. Okay. You need to find out for this energy level, right? What are the wave functions possible? And using that, you need to identify which one among these four, which one is correct. Okay. Listen, for particle in cubical box, for particle in cubical box, okay, energy formula, we write energy E is equal to nx square plus ny square plus nz square times h square by 8ml square, correct? This is how we write. Normally in chemistry we use h by 8ml square as in the energy formula. But in physics, see, this question appeared in 2024 December physics question. It's a physics question. In physics, instead of h, they'll use h bar or h cross. So I'm going to write the same formula in terms of h cross. How? Very simple. Multiply numerator and denominator by 4 pi square. Very simple. So nx square plus ny square plus nz square. I'm going to multiply the numerator by 4 pi square into h square and multiply the denominator, okay, by 4 pi square. I'm multiplying numerator and denominator by same quantity, so the equation doesn't get affected. Okay, now what to do? Let me write the next page. Now what to do? See, you can write this as equal to nx square plus ny square plus nz square times 4 pi square 8ml square. You can cancel this also. 1 4s are 4, 2 4s are 8. See, h square by 4 pi square can be written as h cross square. Am I right? H square by 4 pi square can be written simply as h cross square. What is h cross? Or h cross is nothing but h
6 by
cross
2.
2 pi. It just take
2 pi.
square. On squaring this, we'll get h cross square, which is nothing but equal to h square by 4 pi square. Correct? So the formula is nx square plus ny square plus nz square into pi square h cross square by 2ml square. Yes, this is also can be given. Okay, this type of formula also can be given. So do remember this formula also. Okay, if energy formula has pi quantity and h cross, okay, you should know that this formula is changed in a little bit. Okay, this is how we write in chemistry, but physics people, they normally prefer this. Okay, now what we have to do? What is the energy given? The energy given in this problem is 7 h 7 I'm sorry 7 pi square h cross square by m into a square. This is the energy given. Okay, now what to do? H cross square cancel. Sorry, pi square cancel, h cross cancel, m cancel. I'm sorry, I have given box length as L here, but in the problem it is given A, so it should be A square. So A square cancel. Therefore, nx square plus ny square plus nz square should be equal to, bring this to this side, 7 into 2, 14. Okay, so this square of these numbers should be equal to 14. So what is the probable values for nx, ny, and nz? Probable values. So probable values are 1, 2, 3, right? So nx can be 1, ny can be 2, nz can be 3. This will give me a state. So this is psi 1, 2, 3 state. We can also write psi 1, 3, 2. We can also write psi 2, 3, 1, psi 2, 1, 3, psi 3, 1, 2, psi 3, 2, 1. All these 6 states have the same energy, 7 pi square h cross square by m a square. All these 3 states. Now all these 6 states. Okay. Now out of these 6 states, which one is available in the option we should see. Okay. Right. So wave function. Right. Listen. What is the wave function formula? You know very well. Let me write here. What is the wave function formula? Wave function for particle in cubical box equal to square root of 2 by not square root of 2a, sorry, 2 by in this question this box length is given as a, so I'll write 2 by a whole power 3 by 2, okay, into this is the general formula, sine nx pi by a into x into sine ny pi by a into y, then sin nz pi by a into z. This is the general formula. Now in the place of nx you put 1, ny you put 2, nz you put 3. Okay, if you put 1 here, 2 here, 3 here, then it is psi 1, 2, 3 states, psi 1, 2, 3. Okay, but 6 different possibilities are there, so we have to check which is correct here. Now just go to the 4 options. In all the 4 options, see, the normalization constant is same. Normalization constant is same, so you need not worry about normalization constant. Now see, all these 4 options have sign, 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 sign. Okay, good. Now see the number. Okay, here n equal to 1 here, nx is 1, ny also 1, n is at 2. Is it correct? Is this correct? So you have to check the option
Option C.
in which the quantum number should be 1, 2, 3. So which is correct?
C, sir.
Option C. That's all.
C option.
That's all. Good. This question appeared in 2024 December in physics paper. Okay. Take note.